Good morning. Today we have a rainy, icy, very gray morning. And you can tell that it's rainy and icy because I'm wearing a hat, but I'm also wearing shorts. So that's the first thing. The second thing is that in the laboratory, not just considering microscopy, and in fact, to a large extent, not considering microscopy, we're going to be familiarizing ourselves with exponents and also the metric system. And this is something that is going to be considered on the exam, as you'll see when you watch the lectures. So what I'm going to start out with is talking about the metric system and various units that are associated with the metric system and microscopy that we should be interested in and concerned about. But first I'm going to talk about the exponents, or the use of exponents. So once again I'm going to search for chalk. So exponents. So exponents that we're going to be working with are all going to be based on 10. So these are what are known as orders of magnitude. And this is something that microbiologists typically have to be reasonably well familiar with. And the reason for that is that, first of all, base 10 is something that we're familiar with. But secondly, with microbiology, often we have to consider things that span many orders of magnitude, that is, many powers of 10. So not just 10-fold, but 100-fold, or 1,000-fold, or even 1,000,000 or 1,000,000,000-fold. And in order to wrap our minds around numbers like that, especially when we're starting to compare numbers that are really big with numbers that are quite small, it becomes difficult to do that with just a linear system. And so we tend to think about things in terms of, instead, exponents. And the flip side to exponents are logarithms. And in fact, logarithms make it easier to work with exponents. We already talked a little bit about logarithms when we talked about pH. But let's start by talking about exponents. So exponents. So we've got a base of 10. And then we'll start with the exponent of 0. So this is the weird one. So 10 raised to the 0th power is equal simply to 1. In fact, anything raised to the 0th power is equal to 1. Note that it is not equal to 0. In fact, 0 is not really found in these exponent-based systems. Everything, when we're talking about exponents, 10 raised to something, is going to be something between 0, but not including 0, up to positive infinity. So starting with 10 to the 0. So if we go up an order of magnitude, then we have 10 to the 1. 10 to the 1 is equivalent to 10. So if you multiply 1 by 10, you get a 10 of course, but if you multiply 10 to the 0 by 10, you get 10 to the 1. So 10 to the 1 and 10 are equivalent. And going on in this direction, 10 to the 2 is 100. So if you were to dilute something, which is something we're going to be considering, 100-fold, it's the equivalent to dividing by 10 to the 2. But there's an easier way to represent that, and that is to go over onto this side. So if we are going to divide by 10, so if we're going to divide 1 by 10, that gives us 10 to the minus 1. So 10 to the minus 1 is equivalent to 0.1, which is equivalent to 1 divided by 10. 10 to the minus 2, that's equivalent to 0.01, and that's equivalent to 1 over 100, 1/100th. So you can see, if we took 10 to the 2, and we flipped it under 1, so we divided 1 by 10 to the 2, that would be equal to 10 to the minus 2. Okay? So there's a symmetry here of sorts. If you take something that has a positive exponent and you divide that into 1, then you get the negative exponent. And the opposite is true as well. If you took 1 over 10 to the minus 2, that would be equal to 10 to the 2. Now when you're working with exponents, the wonderful thing is that if you are multiplying things with exponents, so 10 raised to something, so for example, 10 to the 2 times 10 to the 2, what does that equal? Well, it equals 10 to the 2 plus 2, which of course equals 10 to the 4. So each time we've got, so this is, I should show that more fully. So 100 times 100 equals 10,000, which is equal to 10 to the 4. 1, 2, 3, 4 zeros. We can do the same when we're working with negative exponents. So 10 to the minus 2 times 10 to the minus 2 is equal to minus 2 plus minus 2, which is equal to 10 to the minus 4. So this is 0.01, that is 0.01. You multiply the two together and you have 0.001, 3 zeros, which is the equivalent of 1 over 10,000. Now when we're doing dilutions, we're going to be looking at these sorts of things, and the more familiar you can be with these sorts of things, the better. There's another aspect of using exponents, and that is scientific notation. So scientific notation, I know from experience, is something that drives people pretty crazy. But with luck, it won't. And the reason for that is that using scientific notation makes life really, really easy. Well, maybe not life, but it makes working with big numbers much easier. Also working with small numbers much easier. And that's because it puts these numbers in a standard form, and it does so using exponents. So if we had 3, I right away want to do this in a scientific notation form, but I'm resisting it. If we had 3 followed by 1, 2, 3 zeros, that would be the equivalent of 3 times 1,000. And 1,000, because we've got 1, 2, 3 zeros, we know we can write as 10 to the 3. And so this would be equivalent to 3 times 10 to the 3. So 3,000 is really 3 times 10 to the 3. That is scientific notation. If we had 0.003, so this becomes a little more difficult to conceptualize, but bear with me. That would be the equivalent to 3 times 0.001. But we know that 001, or 0.001, is equal to 10 to the minus 3, and therefore 0.003 is equal to 3 times 10 to the minus 3. Now I didn't put a decimal point in here, but if we had 3.24, I want to do scientific notation. Let's start again. If we had 3,240, that would be equivalent to, and here comes a decimal point, 3.24, and we'll put that 0 in there, times 1,000, which would be equal to 3.24 times 10 to the 3. So 3,240 is equal to 3.240, maybe the 0 should be there, maybe not, times 10 to the 3. If we had 4 times 10 to the 8 cells per ml, what would that be equivalent to? Well, the answer is that it would be equivalent to whatever that is times 4. What is that? Well, that's going to be 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, and then a 1. There are little commas in there. So that's 100 million. Now I can do that in my head because I know 10 to the 6 is a million. And 10 to the 8 is 2 in the exponent higher than 10 to the 6. So it must be 100-fold higher than 10 to the 6. It must be 100-fold higher than a million, so it must be 100 million. So this is going to be 4 times 100 million, or 400 million. Now you can write it out as 4 times 1 and all those zeros. You can write it out as 400 million. But it is so much easier to just say 4 times 10 to the 8th. And that's what microbiologists do. Now if you had a 100-fold dilution of this, 4 times 10 to the 8th, you could say, well, we would take away those 2 zeros, move those commas. That would be, what is that? Yes, that's 1 million. And so therefore it would be 4 times 1 million, which would be 4 million. But maybe we could write it out as like that. To me, that's absolutely awful. But if I said a 100-fold dilution of 4 times 10 to the 8th, well, that's easy. That's 4 times 10 to the 6th. How did I come up with that? I simply took 4 times 10 to the 8th and subtracted 2 for that 100-fold dilution. Remember, 100 is equivalent to 10 to the 2. So working with exponents makes life easier, at least if you're a microbiologist. And if you're doing dilutions without exponents, how do you even do that? I don't know. But the other thing that exponents are important for is understanding the metric system. So why is that? Well, it's the same reason that exponents are good in the first place, and that is that exponents are great for understanding big numbers and small numbers, or when comparing big numbers with small numbers. And the metric system basically is a way of comparing big numbers with small numbers. So the metric system, depending upon what measurement you're making, in this case we're going to be using length. The metric system is based on the meter. The meter happens to be 1,000 millimeters. It is also equivalent to 0.001 or 1 over 1,000 or 10 to the minus 3 kilometers. Which is another way of saying that a kilometer is equal to 10 to the 3 meters. 1,000 meters. 1, 2, 3 zeros. In microbiology, typically, we don't care about kilometers, although there are fungal mycelia which take up a phenomenal amount of area as these big giant clones of fungi. But usually in microbiology, kilometers are not something we're thinking about. In fact, meters are not something we're thinking about. And even millimeters, which are 10 to the minus 3 meters. Even millimeters can be pretty darn big from the perspective of microbiology. Yeah, so you're measuring the width of a colony on a plate, and sure, that'll be in meters, but there are so many cells that are making up that colony. Perhaps 10 to the 7 cells. What is 10 to the 7 cells? 10 to the 7 cells is 1 in the exponent bigger than 10 to the 6 cells. How many cells is 10 to the 6 cells? It's a million cells, so 10 to the 7 cells is 10 million cells. That's a lot of cells to get 1 millimeter. Well, maybe a little bit more than 1 millimeter. Maybe it'll be 2 or 3 or 4. Millimeters. So we've got a table, at least in this edition of the book, it's table 3.1, and it goes through all of these things. So centimeters is something that's also useful in the metric system. A meter consists of 100 centimeters, which is 10 to the minus 2 meters. Centi refers to 100, milli refers to 1,000. But usually, when we are talking about microbiology, we're more concerned about micrometers. Micrometers, we abbreviate using the Greek letter mu, which looks like a U. Micrometer. A micrometer is 1/1000th of a millimeter. And a millimeter is 1/1000th of a meter. So how many meters is a micrometer? Well, it's going to be 1/1000 times 1/1000. Or you could say 1/10 to the 3 times 1/10 to the 3. Or you could say 10 to the minus 3 times 10 to the minus 3, or you could say 10 to the minus 3 plus minus 3, or you could say 10 to the minus 6, or you could say 1/millionth, or you could say that there are 1 million, or 10 to the 6, micrometers in a meter. So 10 to the minus 6 meters is equal to a micrometer. 10 to the minus 6 meters is equal to 1, which is equal to 10 to the 0, micrometers. 1 micrometer. So if you had a meter, that would consist of 10 to the 6 micrometers. Okay? How big is a micrometer? Well, an E. coli cell is roughly a micrometer long. So a micrometer is a measurement that is roughly the size of a bacterium. Some bacteria are bigger than that. Some bacteria are smaller than that, but it's roughly the size of a bacterium. A micrometer tends to be relatively large compared to the size of a virus. A virus tends to be, or viruses tend to be small. There are some exceptions to that. There are some viruses that are quite big, but for the most part, a micrometer is small relative to a virus. We also have a measurement that is 1/1000th of a meter. So we also have a measurement that is 1/1000th of a micrometer. So this would be 10 to the minus 3 times 10 to the minus 3. So that would be a millimeter, that would be a micrometer, times 10 to the minus 3 is equal to 10 to the minus 9. So 10 to the minus 9 meters is equal to a nanometer. This is much easier to abbreviate, it's just NM. MM, CM, mu, M, NM. Nanometers are small, but when you're talking about a molecule, a nanometer and say glucose are not too different in size. When you're talking about atoms, however, then you tend to talk about something that's even smaller than a nanometer, and that would be an angstrom. So 10 to the minus 10, so how much is 10 to the minus 10? If 10 to the minus 9 is 1 over a billion, then 10 to the minus 10 must be 1 over 10 billion. So 1/10,000,000th of a meter is equal to an angstrom, which is a person's name. Apparently angstrom, the term comes from Swedish, and this is a Swedish letter. It's A with this circle on top. So when we're talking about atoms, we often can talk about the scales of angstroms. Turns out that while an angstrom is considered to be part of the metric system as 10 to the minus 10 meters, it is not part of the international system, there we go, International System of Units, or SI. So we're talking about angstroms. We can't talk about SI units, but we don't really care about that. But if you're looking at the scale of microorganisms, you're talking about things that are on the order of a micrometer. 10 to the minus 6 meter, 1/1,000,000th of a meter, 1/1000th of a millimeter. And typically centimeters don't come into play. I mean, if you're measuring the size of a zone of inhibition, it might be a centimeter or two or more wide. We might express it in centimeters, but you can just as easily express it in millimeters. But the size of a microorganism, such as a bacterium, such as E. coli, is going to be roughly 10 to the minus 6. And the size of a virus often will be 1/10 of that, 1/100th of that. And then if you get to 1/1000th of that, you're getting to the size of individual, not necessarily very large molecules. And then 1/10-fold further smaller, and you're talking about the size of atoms and the bonds between atoms. So that is the metric system, and that is exponents. And again, exponents, scientific notation, these things make your life easier. They're not just there to mess with your mind. They truly are something that people use not because they're perverse, but because it makes life so much easier. And when you start diluting, when you're diluting over multi-10-fold units, it just becomes much easier to work with exponents. Because then you just add and subtract rather than multiply.